Welcome back to linear algebra. Let's go ahead and jump into Anki. One flashcard. What do we got? What are the 9 chapters of elementary linear algebra by Anton Call? Linear systems and matrices. Determinants. Euclidean vector spaces, general vector spaces, eigenvalues, and eigenvectors. Inner product spaces, quadratics and diagonalization, general linear transformations, numerical methods, general linear transformation, diagonalization, quadratic forms, inner product spaces, eigenvalues and eigenvectors, general vector spaces, Euclidean vector spaces, determinants, systems of linear equations, and matrices. Good. I'm going to go ahead and grade what I did yesterday and then go from there. Okay, so we got both of the proofs from yesterday correct. Again, at this point, I'm still just going for validity, not like eloquence and formal language. I also got the true or false question right, so yeah, what did we learn about yesterday? We started 1.6, which is about more matrix inverses and linear systems, and I think there's a way to solve the note from yesterday was there's a way to solve linear systems using matrix inverses. So let's just go make sure that's correct. We can use the inverse of a matrix to solve a linear system. Okay, so that's that. I'm going to go read, and then I'll be back to recall what I learned in a little bit. All right, that section was actually kind of complex. It was like, don't understand it. Okay, I'm understanding it. Okay, I got it. Like with multiple different concepts. First section was about number of solutions for a linear system, right? We can have 0, 1, or infinitely many. And it presented a proof for that. And the proof was kind of hard to understand at first, but now I think I can explain it. Basically, they're trying to prove that a matrix either has 0, 1, or infinitely many solutions. And it basically was saying, okay, well, if we can show that if the matrix or the linear system has more than one solution, then it has infinitely many solutions, then that will be enough to prove it. For some reason, we can just assume that we know that there's no solutions or one solution. Those are things that you can already know. So what do? We use the matrix, or we use the equation AX equals B, where A is a coefficient matrix, and what is the X called? A variable matrix or something along those lines, and then B is the constants. So let's say that A or X0 is a major, or X0 is an arbitrary solution set. It could be any potential solution of matrix A, or it could be any potential solution set, yeah. So let's say that the X0, an arbitrary solution set, equals x1 minus x2, where they are both distinct solutions, solution sets of matrix or the linear system. Then we can say, okay, ax0 equals b. Okay, let's plug in x1 minus x2 for ax equals 0. Okay, then let's distribute. So now it's ax1 minus ax2 equals b, and ax1 and ax2 are both going to equal b. So because that's just what ax equals b, we already know that, so we can say b minus b equals 0. So we showed that AXO or AX0 equals 0. Okay, now let's say let's just say that A times the sum of x1 plus k being any scalar times x0. Okay. Let's see if we can show that this works out. So there's that. Let's distribute out. So now it's going to be a times x1 plus a times k times x0. So then we have a times x1 plus, let's take the scalar out and move the a in, so commutative and associative properties of the scalar and matrix. So k times the product of a times xo. Then we know that axo equals 0, so we can say that ax1 plus k times 0 equals what? Equals b? Well, ax1 will equal b. So b, so b plus 0, k times 0, which is 0, equals b. So we showed that a, and then the sum of x1 plus k times x0 is equal to b. So we can say that k1, or x1 plus k times x0, this is equal to a solution x, and therefore k can be any value of any value, maybe non-zero value, but there's infinitely many k's, and so k times x0 plus x1, ax1 is a solution set, but then you can substitute anything for k. So that's how we show that there's infinitely many solutions. All right. Okay. So we can solve a linear system using matrix inversion. If we say ax equals b, well then the solution x is going to be equal to the inverse of a times b, pretty simply. So as long as you can find the inverse of a, it's going to have exactly one solution. That's going to be the inverse of a times the matrix b. And so that's the third way we've now learned how to solve a linear system: Gauss-Jordan elimination, Gaussian elimination. If invertible, then we can use matrix inversion. Okay, and now we also learned a way to solve a sequence of linear systems if they all have the same coefficient matrix. We can partition A with all the different B's and then solve via Gauss-Jordan elimination all at the same time. So that might be the most recalling I've done for math or for linear algebra so far. Linear systems. So that works even if the matrix isn't invertible because we're using Gauss-Jordan elimination. Boom. All right. Okay. That's it for today. Talk to you tomorrow. See ya.